In this video, we're going to use the derivative of these these vector valued functions to calculate some different aspects of an object and its motion. So let's talk about speed first. We know in the rectangular coordinates, the absolute value of velocity is the speed of the object. Because we're concerned about the change in distance over time when we find speed, but not the direction in which the object is going. So when we're looking at the speed for a vector valued function, let's take a look. Let's just graph this first. So here we've got a position function r of t and its velocity. So if we look at the velocity vector, so start here, we know that the x component, or the horizontal component, is x prime of t. The vertical component is y prime of t. And this velocity vector is the result of that. So we can see the direction the velocity is, so the direction of the object, and the length of that vector will tell us how fast that object is going, so the speed of that object, and we can see that the direction is also there too. But when we're looking at speed, we're only concerned about the change in the position. So we're going to find the length of that velocity vector in order to find the speed. So the speed is the length, we use a word for that, it's called the magnitude of the velocity vector. Okay, since this is a right triangle, the x prime of t vector is horizontal, the y prime of t vector is vertical, so we get a 90-degree angle. We can use the Pythagorean theorem to find that speed, or that magnitude. So the speed, now to note the magnitude, we use these two bars. The speed will be the magnitude, or the length, of the velocity vector. And in this case, that will be the square root of x prime of t squared, a squared plus b squared, plus y prime of t squared. Okay, let's do an example. Let's find the speed of the original graph that we had up above. So the original function we had up above, s of t, we had 3t squared and t plus 4. Okay, if we find the speed of the particle, let's say at t equals 1. So we're going to find the speed of the particle at t equals 1. Why don't you pause for a moment, see if you can find that yourself, and then come back and we'll do it together. Okay, I hope you gave it a try. The speed of the particle is the magnitude of the velocity of this particle. So that is the square root of the x component's derivative squared. So the derivative of 3t squared is 6t. So if we square that, the derivative of t plus 4 is 1. And if we square that. Now finding the speed when t is equal to 1, we'll just replace t with 1. So 6 times 1 will give us 6. 6 squared is 36, plus 1 squared. So we know that the speed of the particle at t equals 0, at t equals 1, is the square root of 37, whatever the units are. Feet per second, meters per second, whatever the units are. Okay, so that's one application using the derivative of these vector valued functions. Let's look at another. Total distance. So we're going to stick with that same vector that we used up above, and we're going to say that the object's position is given by that vector. So we're going to use that vector to find the total distance this object traveled on the interval from 0 to 3. And when we talk about the interval from 0 to 3, we're talking about time. So from time t equals 0 to time t equals 3. So let's just recall what that graph looks like. The graph crossed the y-axis at 4 and was a parabola in this direction. So if you recall, when time t was 0, that put us right here at that y-intercept, and then time t equals 3 was somewhere in there. And what we're trying to find is the total distance traveled from that point to that point. So what this looks like to me is an arc length question. Since we're trying to find distance traveled, we're trying to find the length of that arc. So let's do that. Let's find the length of that arc. Now, if you'll recall, so total distance equals arc length. And that arc length was from A to B, the square root of x prime of t squared plus y prime of t squared dt. So in this case, we're looking from 0 to 3, the square root of the derivative of x of t, so that's 6t, so that's 6t squared, plus the derivative of t plus 4, which is 1, squared. If we simplify that, that's the square root of 36t squared plus 1. Now if you put that into your calculator, you end up with 27.340 meters, feet, whatever the units are. So the length of that arc is 27.340 meters, or whatever it's measured in. Okay, so that's a second use or second application for the derivative of a vector valued function. I'm going to give you a question now. It's kind of like an FRQ style question. I'm giving you a new position vector this time, and I want you to answer those 3 questions about this vector. So I want you to pause. I want you to find the velocity acceleration vectors, the acceleration vector at t equals 0, and then the speed of the particle at t equals pi, and do not use a calculator. Okay, go give it a shot. Welcome back. I hope you took your time doing this. So we're going to find the velocity vector first. The velocity vector is the first derivative of the position. So in this case, it's the derivative of e to the t, which is e to the t, and the derivative of sine 3t, which is 3 cosine 3t, using the chain rule. There we go. That's the velocity vector. Nothing else to it. That's it. That's the vector that tells us the rate of change of this object. Now to find the acceleration, that is the second derivative of the position function. So I'll differentiate the velocity. So derivative of e to the t is e to the t. The derivative of 3 cosine 3t is negative 9 sine of 3t. There's the acceleration vector. Okay, part B. We're going to calculate the acceleration vector at t equals 0. So we're going to take that acceleration vector we found in part A, and we're going to replace t with 0. So this will become e to the 0 and negative 9 sine of 3 times 0. E to the 0 is 1. Sine of 0 is 0 times negative 9 is 0. So what that's telling us is that this acceleration vector is only in the horizontal direction. There's no vertical change for the acceleration. Okay, finally, we're going to calculate the speed of the particle at t equals pi. So the speed of the particle is the length of that velocity vector, or the magnitude of the velocity vector. So if we find the magnitude of the velocity How long is that velocity vector? That's the speed. That wasn't a very good square root, but we get the idea. We're going to take the derivative, so x prime of t, which is e to the t, and square it. And we'll take the derivative, so of the x, or the y component, sorry, I do have words. So that's 3 cosine 3t, and we'll square that. So this is the magnitude. Now the question's asking what is the magnitude when t is pi. So in other words, what is the speed at this moment in time? So we're going to replace all of the t's with pi. We end up with e to the pi squared plus 3 times the cosine of 3 pi squared. Doing a little bit of calculations just in case this were a multiple choice question. E to the pi squared is e to the 2 pi. The cosine of 3 pi is -1. -1 times 3 is -3. -3 squared is 9. And that's good there. You can leave it like that. If they ask you to simplify it, you would just put that in your calculator. Okay, that was good. Now, let's take a little diversion on these application problems and let's talk about integration for a moment. So if we have a position function, or I guess in this case this looks more like a velocity function that is made up of f prime of t and g prime of t. Well, then the antiderivative of that vector is found by just taking the antiderivative of each part separately. And when we do that, we end up with f of t plus some constant and g of t plus a different constant. So that part is really important to remember. When we find the antiderivative of each part, they each have their own constant of integration there. Okay, now if we're looking at the definite integral from a to b, we'll still use the first fundamental theorem of calculus. This will be f of b minus f of a, and this will be g of b minus g of a. So nothing different there. Okay, we're going to use this idea to solve this problem. Now this one's a little bit different because I've given you the vector in unit vector form. In other words, there's I and j in this vector. So let's take a look at everything that we've got here. We've got the second derivative vector is -4 cosine t in the horizontal position, and then -6 in the vertical direction. So if we were to write that in component form, it would look like this. -4 cosine t and -6. That's the x and the y components. Okay, let's look at the other vectors that are given to us. We have the r prime vector. So r prime of 0 is 3j. Notice there's no I component there. So we know that r prime of 0 has a 0 component for the I, or a 0 value, and 3 for the j. So 3 for the vertical. So another way of saying this is well, this is good enough. Well, let's do it. That x prime of 0 equals 0, y prime of 0 is equal to 3. And with that same idea in mind, r of 0 is equal to 2i. Another way of saying that is that r of 0 has a 2 for its horizontal value, but 0 for the vertical value. So that we know then x of 0 is 2, and y of 0 is 0. Okay, that's a lot of information, and that's really good to know. I'm going to shrink this down because I didn't leave myself enough room, but that's really good information to have. I'm going to move things around a little bit so I've got some space here. So I'm going to put this here. That's good to hear, or good to know. I don't really want any of this right now, but this is important. And I'm going to remove all of this for now, and this is important. Okay, I'm going to do the first step. The first step, we know the second derivative, so we're going to find the first derivative because the question's asking us to find the r vector, the original position. So we're going to work this backwards. We're going to take that second derivative function and we're going to integrate it. So first off, r prime of t, I'm going to find the x component first. So I'm going to find x prime of t first. So x prime of t is the antiderivative of negative 4 cosine t. The antiderivative of negative 4 cosine t is negative 4 sine t plus some constant. So now this is where the information, the original information that was given to us, we know that x prime of 0 equals 0. So we know that 0 equals negative 4 sine of 0 plus c. Sine of 0 is 0, so all of that being said, c is 0. So we know that x prime of t is just negative 4 sine t. Okay, if I use the same idea for y prime of t, I'm going to find the antiderivative of negative 6. The antiderivative of negative 6 is negative 6t plus a different constant. I know the information that was given to us is that when 0 is plugged into the y component's first derivative, that will equal 3. So we know that 3 is equal to negative 6 times 0 plus c sub 2. So c sub 2 is 3. So now we know the y component. We have negative 6t plus 3. So all of that being said, now we know r prime. We know the r prime vector is negative 4 sine t and negative 6t plus 3. Okay, we would do the same thing then. We're going to do the same thing to find r. We're going to find the antiderivative. And I really did not leave myself enough room, so I'm going to shrink all of this down that we've done so far and leave some space so that I can find r. Okay, let's find r then. We're going to find the x component and the y component. So we know that x of t will equal the antiderivative of negative 4 sine t. Antiderivative of that is 4 cosine t plus some constant. The information that was given to us is that x of 0 is equal to 2. So I know that 2 is equal to 4 cosine of 0 plus some constant c. Cosine of 0 is 1. 1 times 4 is 4. So I know that this c value, c sub 1, will be negative 2. So if I write this in, 4 cosine t minus 2. Okay, last but not least, I'll do the same thing now for y. I'm going to find the antiderivative of negative 6t plus 3. That's negative 3t squared plus 3t plus a second constant. The information given to us is that y of 0 equals 0. So I'm going to plug all of that in here. C sub 2 equals 0. So this just becomes negative 3t squared plus 3t. So finally, after all of that work, that was a lot of work, we get the original vector. The original vector was 4 cosine t minus 2 and negative 3t squared plus 3t. That was a long one, but it was good. Okay, the last question then is this. Particle's position in the xy plane is given by x of t, y of t. For t greater than or equal to 0, we have the first derivative and the second derivative. So we have x prime and y prime. And some information is given to you. At t equals 0, we know x of 0 and we know y of 0. So I'd like you to first find the position of the particle at t equals 3, and then find the total distance traveled over that time interval. So pause this, go give it a try. Okay, I hope you tried. This one's a little different than the last one in that it's asking us to find the position of the particle at t equals 3. So what we need to know then is that we need to know the original position. So we have the derivative. If we find hold on, let me just write it this way. So we're saying, what is x of 3 going to be equal to? Well, we started when t equals 0, we started at an x value of 0. Then finding the displacement from 0 to 3. So we're going to find the antiderivative of dx dt from 0 to 3. To find the y value, we know that y started at negative 4 when t was 0. So if we add on the displacement, how much that changed from 0 to 3, that'll give us the final location for the y coordinate. So putting that as in your calculator, in the first one we end up with 21, and on the second one we get negative 3.226. The question said, what is the position at that time? So the particle's position at t equals 3 is 21, negative 3.226. Okay, the total distance traveled, we've already talked about that. The total distance traveled is the arc length. So we already have the derivatives. Be careful, don't find the derivative again. So we already have the derivatives, they've been given to us. So we're going to take just the area from 0 to 3, or not the area, but the definite integral from 0 to 3 of the square root of the first derivative squared plus the first derivative of x squared plus the first derivative of y squared. That's the total distance traveled. That's the length of the arc. And if we type that into the calculator, you get 21.091. That's the distance traveled. Okay, that's it for this unit. There's a lot to it, but luckily there's a way you can kind of make sense of these things. Keep trying to make sense